pressure. But I'll try to include some new elements, and I promise I'll give a different talk next time. So I'll talk about, I'll kind of start with a broader picture maybe. I'll try to discuss metastability in general, and this philosophy that is promoted by Friedland about what the correct state space for an effective system should be.
Oh.
And we are talking about so let me start with several examples, simple examples, sort of trivial. First, let's talk about unperturbed system being a Markov chain. And let's say it just has two states, right? So let's say in unperturbed state, there's no motion at all, right? So that in this case, there are two states and two invariant measures, two different ergodic invariant measures, right? You can have invariant measures concentrated in state 1, or you can have an ergodic an invariant measure concentrated in state 2. And of course, any linear combination works, right? If you allow some perturbation, some small amount of motion, so with intensity epsilon, or let's say this is probability of a jump in unit time. And epsilon here. You can think of continuous time Markov chain. That's why I said in unit time. So maybe probability of a jump in not in unit time, I should say, then in time delta is approximately delta times epsilon, right? And the same way on the same thing on the way back. So this is kind of an infinitesimal. So this is jump rate then, not jump probability, jump rate. If you're talking about continuous time Markov chain, or if you're talking about discrete time Markov chain, you jump in place with overwhelming probability, or epsilon or epsilon is the probability of a jump. Okay, so everybody is familiar with this. Then you immediately get the invariant measure is the invariant measure is 1/2, 1/2, right? Because everything is completely symmetric. 1/2 here and 1/2 in the other state. Well, we're familiar with the ergodic theorem. That is that to see this invariant measure, you need to wait for a long time. So limit as t goes to infinity of let's say position at time t, no matter where you start. Let's say you start at position 1. Is a limit probability that this is equal to 1 is equal to 1/2, and the same thing is equal to 2 is equal to 1/2. But that you need to wait for some time. How long do you need to wait? If you wait for a long but long amount of time, which is dependent on epsilon, you don't see the invariant distribution. You see something else. If you say limit as probability that you start for location 1 and wait for time 1, sort of epsilon to the power minus 1/2, then you'll not move. You'll just see the place where you are, right? And that's it. So you need to be careful when applying this this ergodic theorem in the situation where the time when you observe the system and there is some small parameter in the system when they're dependent, right? So that's kind of a trivial example. Another trivial example you can get by considering a Markov chain where the transition rate, let's say in one direction it's epsilon, and in the other direction it's much smaller, epsilon sorry, epsilon to the power 2. These are transition rates or transition probabilities, if you wish. If you prefer discrete time Markov chain, then the complement is the probability of staying in place during 1 unit of time, right? And then you may have some more complicated behavior. For example, you start at 1, limit as in the first case, you see, the first limit, I said limit as t goes to infinity. Here I should say, because epsilon t are dependent, I should say epsilon goes to 0. Time then automatically is adjusted, right? So in the situation with epsilon to the power 2, we have limit as epsilon goes to 0. If I do probability, for example, x, again, epsilon to the power minus 1/2 equals to 1, that's 1. Limit as epsilon goes to 0, probability at epsilon, let's say, so x starting with 1 at time epsilon to the power minus 3/2. So what happens at time epsilon to the minus 3/2? You have enough time to go from 1 to 2, but you don't have enough time to come back. Because time to make a transition, time to jump, is of order epsilon to the minus 2. So at this rate, you don't go from 2 to 1. So if you look at this probability, it's just 0, right? And even if you replace this epsilon to the power minus 3/2 by epsilon to the power minus 10, then what happens? In a very long time, you go from 1 to 2, then you have enough time to come back. You make a lot of these transitions, but actually you can calculate the invariant measure. The invariant measure is almost 1 here. It's like 1 minus epsilon and epsilon of this order of magnitude. Maybe I need to adjust this a little bit, but approximately epsilon, approximately 1 minus epsilon. So so what do we have? We have this invariant measure that depends on epsilon. That's the genuine invariant measure, but you have metastable distribution. So at different times, you see different limits. At time epsilon to the power minus 1/2, the metastable distribution is concentrated in the first point, and at larger times, at times much larger than epsilon to the power minus 1, the metastable distribution is concentrated at the second point. So this is the phenomena that I want to observe in various more complicated systems. But here we already see the basic example, and we see that different states. What are the states? The states are here just 1 and 2, but each of them carries an ergodic measure of the unperturbed system. The unperturbed system is the one I started with, where you just have 2 points and they don't, there's no motion there, right? That's unperturbed system. So let me discuss a few more examples, some kind of classical, some that we are going to maybe, hopefully they'll become classical as we make more progress and popularize them more. So Freyden-Wenzel theory, what is that about? You have a dynamical system, and maybe it has different there are different equilibria, and maybe there are different equilibria here. So let me make these red. These are, say, stable equilibria. Maybe let's make another one blue. This whole curve is maybe a kind of a limit, it carries a measure, but it's not stable. The dynamical system if you start it near this blue curve, it will go away. There may be other stable curves or points here, like this, right? So, and let's call them whatever, S1, S2, S3, S4. So these are the asymptotically stable equilibrium or limit cycles. And then each of them carries an ergodic invariant measure for the unperturbed system. The unperturbed system is just the dynamical system. And then one can study this dynamical system. Let me write it schematically like this. D of xt is equal to V of xt dt. I purposefully write it not in the form of ordinary differential equation because I want to add a stochastic term. But before stochastic term, I can just divide by dt, right? It's an ODE then. But I can add epsilon dwt. In this case, it becomes a small perturbation of the dynamical system. And what happens is that then these individual invariant measures get destroyed because you have maybe just one invariant measure. If it's for a fixed positive epsilon, this is a non-degenerate diffusion. But still, you have different types of limiting behavior. You have, I'll maybe in this particular example, I'll go in a slightly more detail in a few minutes. But you have limit as x. Let's start somewhere at some point x here, the initial point near S1, for example. Starting from x1, I need to observe for time that depends on epsilon. And I cannot say it's equal to S1. It's never going to hit an individual point, but maybe it belongs to a small neighborhood ball of radius delta around S1 as epsilon goes to 0. I can talk about the limit. Of course, so now what does this t need to be? This t needs to be sufficiently large if I want to move somewhere close to S1. And delta is a fixed number. Delta, I don't know, 0.01. But if I wait too long, then the diffusion will give me a chance to escape. So I'll see different possible limits in this case, depending on t of epsilon. And in a way, I'll recover the picture similar to what I drew before. It's going to be kind of a Markov chain. Markov chain with well, maybe a slightly more general situation than just a Markov chain, because I'll not be jumping from a point to point. I'll be jumping from a tiny neighborhood of S1 to a tiny neighborhood of S2 to etc. Maybe back and forth. So certain cycles will form. Again, it's going to be kind of depending on the time scale, it's going to be a different limit. And the distribution will depend on the initial point, the time scale, and so I'll return to this picture. Describe it.
Something happened to your audio. Is it only for me or everybody?
No, for everybody, I think. It is very low.
Very low.
Oh yeah, now
it's
fine.
It's back.
Okay, sorry. Yeah, I don't know.
Just by the way, a question: if the blue curve is invariant for the dynamical system, not stable but invariant. If I consider without the perturbative.
Yes.
Yes. Okay.
And what do we see in the end? We see a picture where the effective motion, or basically we can talk about different limits, right? We can talk about so basically what are we studying? We are studying limiting measures for x t of epsilon with different t of epsilon. These limiting measures, they evolve on the space that coincides with the set of invariant measures of the original system. I mean, of course, I can say it evolves on the set of on a set of red points or red curves, but each of them carries exactly one invariant measure for the unperturbed system, right? So it's a sort of good, sort of philosophically, it's a certain interesting point. Let me give a few more.
Oh, sorry, I have a question.
Uh-huh.
But my question is, so you said after adding the noise, the epsilon are invariant measure. So I guess when taking this limit will be a mixture of the original invariant measures of the unperturbed system, right?
You could, well, we can talk about different, so invariant measure of the, so what is the invariant measure? Invariant measure for fixed epsilon is the same as taking limit as t goes to infinity without regard for epsilon, right? So by the ergodic theorem. So yes, it's going to be highly concentrated near the red points, right? Depending on which of those wells, in a sense, is the deepest, right? It's going to be almost concentrated there.
Right.
It's not going to be a pure mixture because epsilon is fixed, right? But if you what my claim is, if you take t of epsilon and epsilon take to 0, sorry, x, I should say I should include epsilon in the notation of here, right? So x depends on epsilon, right? The process. If I take the process, take epsilon to 0 and take large times, then it's going to be a pure mixture of invariant measures for x without epsilon. So does this answer your question?
Yeah. Yes. So that's right. I was asking about your claim. So depending on how t depends on epsilon, we will get different mixtures, right?
Exactly right.
And so the evolution is kind of with respect. So if t is epsilon to the power of minus alpha, for example, we want to describe how this mixture depends or evolves with alpha.
Exactly. Well, here in the Frey-Levensel picture, it's actually exponential scale. So it's e to the power. So it's going to the scales are going to be not powers but exponents of epsilon.
Okay. Thank you. Yes.
But in some other cases, it's exactly going to be powers or something else, right? So what I want to do, so what is my plan? I'm going to throw in a few more examples where this phenomenon is observed. Each of these examples needs to be analyzed using somewhat different tools. But there are some common features or common things that you can use to analyze them. That's sort of the commonalities I'm going to explore toward the end of the talk. I'm going to put everything in a very abstract framework. But I'll also give tools for analyzing one particular system because those, I believe, are somewhat new tools. Well, new in a sense, the things we developed with Mark Friedlin over the last few years. And some other examples some other people have looked at. Okay. So let me sort of, it's going to have 3 parts. So examples, focus on one particular system, and then sort of an abstract framework. So some other systems, let's do this. You have, this is the one actually I'm going to focus on. You have, again, points, and then you have manifolds, they're invariant, but they're invariant not for a dynamical system, but they're invariant for a diffusion process. dxt is equal to sum vi dwi plus v0 dt. I'll write as Stratonovich form. So this is the unperturbed system, but the unperturbed system leaves S1, S2, whatever, S3, S4 invariant. So it's similar to the Friedel-Wenzel setup, but you have plenty of motion, sort of random motion outside. You just cannot cross these points or surfaces. And then you add epsilon dwt. So I'll not dwell more on this because this is going to be dealt with momentarily in much more detail. That's one example. Actually, there are two examples here maybe because you can talk about attracting or repelling surfaces. In the case they're all repelling, it's a slightly different picture from when there are some of them are attracting. But again, I'll get to that. Another picture. Let's say you have a bunch of domains. Right? And then you have Brownian motion in each, or let's say some diffusion process. dxt is equal to basically dwt and reflection on the boundaries. So that the trajectories will be just basically confined to each domain, right? If you start in domain 1, you don't get out. And then depending on where you start, you'll get your own invariant measure. And then let's do this. Let's connect these domains by narrow channels. Create some openings. I don't know how to erase the walls, because if I start erasing, I'll erase the whole domain. But the idea is the following. Basically, there are channels and there are openings. So like this, right? And openings have size, whatever. You can control the size of the openings. You can do epsilon to the power alpha, for example, right? And then with small probabilities, or rather in very large time, you'll be able to move from one domain to another. And then you'll get distribution on the limiting distribution will depend on the time scale, and it will concentrate on one domain or another, or there's going to be a mixture. And actually this problem, I mean, it has to do with sort of so-called narrow escape problems, sort of a PDE or probabilistic problem, is how long it takes to get to a small portion of the boundary and go through a tube. This has been considered by a graduate student, Wen-Tai Su. He's not my student, but he's a student in our department, Sandra Cherai's student, and he's analyzed this model to some extent. And he's got some good results. So this is another example of when you can observe metastability. And again, you'll see a mixture of the ergodic invariant measures for the unperturbed system. Another example, you have again, so maybe this is going to be some heteroclinic network. So you have a dynamical system of this sort with sort of stationary points. You have dynamics inside each cell. Maybe it goes like this. And in some sense, the dynamics inside a cell, the unperturbed dynamics, it's not a Hamiltonian flow. You can kind of get closer and closer to the boundary, but depending on the nature of these stationary points, they're kind of hyperbolic points. But depending on whether they're more attracting or more repelling, in some sense, you may get a picture where after you include a perturbation, let me write the perturbed system. dxt again is v of xt plus epsilon dwt. it may take a very long time to sort of escape from one cell and go to another, because most of the transitions may happen from between a neighboring pair of cells, and the system will live near one edge, and then only after a polynomial in epsilon time, it will go to another cell. And such things have been considered by Yura Bakhtin and his co-authors. He's in NYU. So that's another system. So what else? By the way, maybe I should mention something where you don't have metastability, but where this phenomenon of motion on the invariant sets of the unperturbed system still takes place. So I'm going to deviate in this one last example. Again, this is due to Friedel and Wenzel. Some of you, or many of you, are probably familiar with this. So let's consider a Hamiltonian flow. So I'll draw this picture. So these are flow lines of a Hamiltonian system, so they go like this. And then the Hamiltonian looks like this. So basically, what are these? This is V of xt is equal to gradient perpendicular of some function h. And the function h has maybe two minima. Has two minima, and it has one saddle point. Here I'm looking at dimension 2. So this is above. I'm drawing the kind of the graph of this Hamiltonian. Below are, so the h is from R2 to R1. And if you look at the gradient perpendicular, it's going to create these flow lines. And you can look at a graph. Graph is associated with function h, and it's obtained by mapping each flow line into a point. And so the saddle point is going to get mapped to a vertex on the graph, and there are going to be two edges going down, and then there's going to be an edge going up. So this is the graph, let's say G, corresponding to h. It's called the Reeb graph of this function h. And then if you look at the unperturbed system, let's look at the unperturbed system. I'll write it here. Dxt is equal to V of xt. Is going to, what is going to be? We are just going along the flow lines of this vector field. So I'll draw them red. I'm just staying in place in some sense. Well, not staying in place. Here on the picture on the left, I'm just making circles. But if I project it on the graph, it's just staying in place, right, in one point. And you see, the unperturbed system has many invariant measures, right? If I start in a certain level set, I'll just stay there, and there's going to be an invariant measure there. So this graph, yes, it is a Reeb graph. That's what we're used to, but it encodes all the invariant measures of the unperturbed system. So that does make sense? So
can you please explain how we constructed the Reeb graph once again?
So the Reeb graph is constructed like this. So we look at the Hamiltonian, right? Hamiltonian is just a function from R2 to R1 in this case. We look at the minimum, right? The minimum is mapped into one point. Then we go up. Each level set, here it is, right? Gets mapped into one point. We go higher and higher until we reach this level where we do see this 8-shaped figure, right? This gets mapped here. So
I understand. So it's always for any Hamiltonian, it's going to be like a tree.
Yes. If the Hamiltonian is defined on a flat surface, right? If it's on R2, if the Hamiltonian is defined on a torus, it may. So let's say here, take a torus, right? I may go down a little bit. Take a torus and put it like this, just on one, sort of put it kind of on the side, right? And h of x is just height, right? Then the graph will look like this. The graph will look like this. So then it's not quite a tree, but it's okay, right?
So the Hamiltonian is mapping from where to where
In this case, it's just a mapping from torus to R. But above, it's just a mapping from R2 to R1.
Ah, okay. I understand. Thank you.
Yeah.
And sorry, how is defined the length of the edges of the graph? It is the 8.
The length is defined according to the size of h. So basically, let's make this mapping. Let's call it gamma. Gamma of any point x is just h of x with some. Gamma of x is the pair h of x. So it's the height h. So and there's a label I. So basically, length is defined according to this function h.
Okay. Mm-hmm.
But I cannot say that 2 points with the same height necessarily get mapped onto the same point on the graph, because a label distinguishes between
Yes.
between different edges to account for the topology, right?
Mm-hmm. Yes.
So, and there are generalizations of this to higher dimensions, and it doesn't have to be a Hamiltonian flow. It can be just basically anything with invariant surfaces, etc. But the point I want to make, I don't want to go deep into this picture. So what I want to say is that just philosophically, the unperturbed motion is just sitting on this graph, just not moving. And points of this graph, they label invariant measures of the unperturbed system. But if you include a little bit of a perturbation, for example, if I write d of xt is equal to v of xt plus epsilon dwt, then what you get effective motion, let's call it. Then if you take gamma of x epsilon t, that's already motion on the graph, right? Of course, you need to speed it up. So you need, because epsilon is small, so you need to rescale time, t over epsilon here. Gamma of x epsilon t over epsilon, it will converge to some limiting motion on the graph, yt. This is a theorem. This can be found in Friedel-Wenzel book, yellow book. But it shows that the limiting motion happens on the set of invariant measures. By the way, there are other types of perturbation possible. So here what I did, I added a little diffusion, another type of perturbation of the same system. So another dx epsilon t is equal to v of, let's just say, xi t over epsilon, very fast. And this is fast diffusion on some set. So that's I should say v of v of x xi of t over epsilon, and that, let me say, v tilde. So you have some vector field which is very fast changing, but that averages, and V tilde averages to V. So in a sense, if you perform the averaging, you see the Hamiltonian flow. If you have before you perform the averaging, you see some very sort of chaotic motion. Here I'll draw it around those yellow. Oh yeah. Around those red orbits, right? So you see some effective motion in the long term. No, okay, and I don't want to go very deeply into this. This actually has been handled by my former student Shou Yan, and he went for a postdoc recently, so he's in the UK. But this just shows that the perturbation need not be additive. And here I stepped away in this last example. I stepped away from considering metastability, but just to illustrate this point that effective motion happens oftentimes on the set of invariant measures, and I brought up this sort of averaging on graphs result by Friedel and Wenzel. This is not the main point of the talk. So, but prior to that, I gave several examples of systems where metastability arises, and sort of this was the motivation. Now let me go to another portion of the talk. Some of you heard that, but I'll hopefully be able to go a little bit deeper since it's a seminar format. And so here I'll share some slides. Let me see. So unless there are questions about this whiteboard, I'll close it. So is everything okay?
Yeah, my question is about your original claim, which I asked you about. Is this the claim we're going to prove, or should it be obvious by now?
The claim that
claim that this with proper scaling we get a mixture, or we get some distribution on the space of the original invariant distribution.
Yeah, so it's not, I didn't make it as in form of a claim. It's more like a philosophical observation, which needs, of course, to be justified in each case separately. So, so I did not make any, I didn't formulate any theorems yet at all. I was just kind of drawing pictures at this point.
Okay, but you're going to get to this in a more formal way later,
yes,
right?
Yes.
Okay,
yes.
thank you.
In a couple of examples, yeah. And as well as an abstract setting where we can try with some effort to fit every scenario. Well, the latest scenario is not about metastability, so that's just a philosophical point for beauty. But so let me see if I close this, and then I need to share screen. I'll share this screen. So here, this again is a screen for talks about Friedel-Wenzel theory. That's kind of, I'm going to talk about small perturbations of stochastic systems, but let me maybe motivate it a little bit more, because this is a very classical thing, Friedel-Wenzel theory. So here we have a dynamical system. I already drew it. Maybe the colors are a little bit different. Maybe this is a neater picture. You have those orange invariant sets, points or curves. Some of them stable, some of them are not. The blue thing is the trajectory of the unperturbed system. The process that we are looking at is now a perturbation of a dynamical system. You can see my screen, can't you?
Yes, fine. Yes.
Yeah, okay, excellent. Yeah, I don't know if you can see the cursor, but when I'm pointing to something.
We can see.
We can see.
Even the cursor, excellent. Yeah, perfect. So we have a stochastic system, which is a small perturbation of the dynamical system. Now, to see something non-trivial, you need to look at times which are exponential in epsilon. So if I look at times which are large, so this symbol much larger means the ratio goes to infinity, right? So if I see t which is much larger than 1 but much smaller than any exponent, what happens is we just go to the closest, nearest stable attractor. So just follow the trajectory of the unperturbed system and kind of approach there. So we need exponential and epsilon squared time to go from one attractor to another. In order to get a qualitative result, a quantitative result as well, we need to understand the times, and we need to understand the probabilities of transitions, and those are governed by so-called values of quasi-potential. They're called, I'll denote them Vij. Ij are labels of those points or limit cycles. So Vij, they are expressed in terms of the so-called quasi-potential. This quasi-potential is the following. For each curve, phi is a curve connecting Si and Sj. For each curve, we can form the following object. We take phi prime of t minus v of phi prime squared and integrate over the time. The curve is defined on the time interval 0t. So basically, we tell ourselves, okay, let's give ourselves some time t to go from one location to another. And then necessarily we'll get some positive quantity S of phi. Why is this always positive? How can it be zero? It can be zero only if phi just solves the ODE, if phi prime is equal to v. So following the trajectory of the dynamical system doesn't cost anything. S of that is zero. But every time we want to do anything different, we have to pay a price. S of phi is the kind of the price we have to pay. And then Vij, we minimize this price over all possible curves connecting Si and Sj. And that's, so then the time to get, so here's the statement, the time to get from Si to Sj is typically e to the power minimum, well, if I fix j, it's just Vij over epsilon squared. So the place where you go first is obtained by minimizing over all possible j's. So this is how you determine the nearest or the next attractor. And you see that the process of transitions between different attractors resembles a Markov chain that I started the presentation with, but with very small epsilon-dependent transition rates, because basically transition rates are the inverse of these quantities. And then generically, there exists a finite number of timescales such that for every initial point and every timescale between these, between lambda k over epsilon squared and lambda k plus 1 over epsilon squared, in the exponential sense, so logarithm of t of epsilon, if it's between those, then we can say that x t of epsilon is found in the vicinity of one particular attractor. Of course, you may have symmetries in the system where you have probability 1/2 or 1/3 to be found in the vicinity of one attractor, and complementary probability to be found in the vicinity of another attractor. You may also ask a question, what happens at exactly the critical timescales? So the transition takes place in a particular way. Right? So, okay, so I hope I motivated a little bit this picture with previous examples. Now we focused a little bit more on this example. So now in a matter of 3 or 5 minutes, I explained the entire Friedel-Wenzel theory, right? Which is several chapters, major chapters in the book, right? So I didn't maybe do a very thorough job out of it, but okay, so this is the picture. If you have any questions. Yeah?
So do I understand correctly? So for example, when we have this t scaling exponentially with the square of epsilon, the going with between attractors is basically similar to a finite state Markov chain, like you said.
Yes.
But so in a finite state Markov chain, usually I guess the invariant distribution does not concentrate on only one vertex. But here is my intuition correct that because the the scales of the transition probabilities are so different. We only concentrate on one attractor. So my question is, why is X found only in the vicinity of one attractor and not a set of attractors that we can get to in this time scale?
Yeah, what you said is exactly correct. So it's because I said generically, right? So it means that the relative strength of these attractors is different. That's why this sort of, remember, I started the very first slide I drew was a Markov chain with two states, right? If the transition rates are epsilon in one direction and epsilon in the opposite direction, then eventually you'll see a distribution 1/2, 1/2, right?
Right.
You start in one, you sit until you have enough time to equidistribute, right? But if transition rates are different, in one direction it's epsilon, and the other it's epsilon squared, right? Then you sit and then you go to another attractor, and then you cannot escape from there. So it's because of lack of symmetry. But if you have symmetries or some kind of, these lambdas may be the same. So then you may have a distribution between, so we may study a situation where you have not a single attractor, but not a metastable state. Actually, in the original book of Friedland, or the original work, because that later they put it in the yellow book, but it was called metastable state because they made this assumption that all of these lambdas are different. But in principle, you could talk about not metastable states, but metastable distributions. So I think what you're saying is exactly correct.
Mm-hmm. Okay, I understand. Thank you.
Yeah, and I'll talk about the situation where you basically in the general picture that I want to paint later, we can deal with metastable distributions. So it doesn't have to be finite number of states with very different parameters, right? Now I'm going to talk about the main result that I want to present concerning a particular type of systems, and this is joint work with joint work with Mark Friedland, and also in the case of repelling surfaces, it's more recent work. It's joint with my graduate student Changlin Liu. The starting point, the unperturbed system, is a diffusion process. So diffusion process, so V0, Vi, dWi. So it's written in Stratonovich form. I'll explain momentarily what it means, because probably people are used to writing diffusion processes in Ito form. But okay, so what it means is that the generator of this, so the V0 is just first order term. It corresponds to differentiation along vector field V0, and Vi dW means the generator is a second order operator, which is second derivative along the vector field. So you differentiate along the vector field, then you differentiate along the vector field again. So of course, if these vector fields, for example, coincide with coordinate directions, then it just becomes a Laplace operator. But I purposefully wanted to be kind of curves rather than some prescribed directions. So the generator can be written like this. Li's are second order derivatives along vector fields. And here's the picture explaining what is going on. If you don't like the previous slide, here's what's going on. You have, I'll assume there are surfaces which are invariant for this process, and then there are vector fields. Here I drew them in different colors, and what happens, you kind of have like a little diffusion along each vector field. V0 is the deterministic part, so you always in time, in a short amount of time, you go along vector field V0, a certain deterministic direct magnitude. And then along each other vector field, you go in the direction of that vector field or in the opposite direction with probability 1/2. This is kind of a random walk version of this diffusion process, right? The same way as you can get a pure Brownian motion out of going right, left, up, or down with equal probabilities. Here we go along each of the vector field or in the opposite direction with equal probabilities, except V0, which you always go forward. So this is the diffusion in the Stratonovich form. This is what it is. And because I assume all of these vector fields are tangent to each surface, you cannot cross the surface. So what are okay? So what do I assume? I assume that on the surface, if I start on each surface, then I just continue living on the surface. Let me assume that the process, if restricted to a surface, is an ergodic process. So you have a measure concentrated on each surface. So this is the set of invariant measures. The surfaces themselves individually label invariant measures for the unperturbed system. By the way, you may have other invariant measures. What are those? They may be invariant measures living inside a surface, right? If a surface is d-1 dimensional, it may bound a piece of space. And with some luck, you may have invariant measures not on a d-1 dimensional surface, but on a piece of d-dimensional space. Not always, but sometimes you may have that. All right. So, and then we'll perturb this system. The perturbation I'll write, so here epsilon squared, I'll include epsilon squared V0 tilde, I'll include epsilon V tilde. So if you look at the generator of the perturbed system, it will look like the original generator plus epsilon squared L tilde, where L tilde is another second order operator. And I'll assume that the second order operator is non-degenerate anymore. So together they form an elliptic operator, or the diffusion they form together, that it goes from any point to the vicinity of any other point. You can cross the surfaces, but very slowly because this epsilon squared is small. And our goal is to understand the behavior of this perturbed system at times that are dependent on epsilon, at timescales t of epsilon. Now, unlike the Friedel-Wenzel case, the timescales are not going to be exponents of epsilon squared, but they're going to be different powers. So the first timescale, well, there's one, so you want to look at times larger than 1, so you want a large times. There's going to be a logarithmic time, because the logarithmic time is needed to kind of initiate the system in a reasonable way, because you may have a situation where you are at a repelling surface, repelling versus attracting, I'll talk about in a moment, but you need time to separate yourself from that. And then the rest are going to be powers of epsilon. And the claim is that if your time scale is between these characteristic or critical time scales, then you can identify a limiting distribution. Actually, I believe we can talk about what happens at the critical time scales, but there notationally, it's a little bit more complicated. So let me say, between the critical time scales, you have a limiting distribution. And then, again, this is here, I think I put it in writing, that the perturbed limits.
Sorry, just a question. If it's a tk epsilon or epsilon minus alpha k, like before with some alpha k, which are distinct and ordered.
Yes, so these tk of epsilon are epsilon to the power alpha k, yeah.
Okay,
not e to the power alpha. So
minus alpha k. Okay.
Yeah, let me see if I can write here. Yeah, wow, amazing. I can even write on the screen. Because I thought it was either or. Either I write or I show a PDF file. But so before, so now these are going to be epsilon. I'll denote them epsilon to the power gamma k. Epsilon to the power gamma k plus 1. Or minus. So these are going to be powers of epsilon.
It is like before, in fact, in the classical case of Friedel-Wenzel, you have some formula, not some formula, but some indication about the values of the gamma k, maybe some variational formula, or I don't know.
So this is what we have now, right? And
yes.
Friedel-Wenzel, we had
Phys lambda k
was e to the power lambda k plus 1 over epsilon squared.
Yeah, no, just the question is, do you have some information about phys lambda k or phys gamma k, or they are just abstract numbers?
Of his or in this case?
In both.
In their case or in our case?
In both, in fact.
In both, yeah. Yes, absolutely. So in the case of Friedel and Wenzel, these lambda k's are related to Vij's. These Vij's are the values of the quasi-potential.
Yes.
And the quasi-potential is determined in terms of action functional. So it's basically you have those wells, right? There's attractor. There's kind of attractors of everything gets attracted here, right? You have this Si, you have Sj, and then you have to figure out how to go from one to another. You kind of need to choose an optimal path. And you calculate quasi-potential along the optimal path. You minimize overall path to calculate these Vij's. And these Vij's are kind of closely related to these lambdas. There's basically some linear algebra that transforms these Vij's into lambdas. It's very simple. For example, if there are just two sets, S1 and S2, then this Vij is exactly lambda. That's in Friedel-Wenzel theory. But you see, what is important in Friedel-Wenzel theory is that you have a whole path. You optimize some function over the entire path, so it's very non-local. This calculation of these lambda k's, and it's not surprising because to move with small diffusion against a vector field, you need to act throughout your journey. You need to optimize your path throughout the journey. Otherwise, the vector field will bring you back. In our case, these gammas, we call them gammas rather than lambdas for some reason. These gammas are determined by what happens in a small neighborhood of the surface. So these are kind of determined locally. Because in our case, when talking about random perturbations of stochastic systems, the most difficult thing is to separate ourselves from a surface. And after that, we have a non-degenerate original system already, which and there the perturbation doesn't matter anymore.
Because in the general case, in Friedel-Wenzel case, usually you cannot compute the quasi-potential except if you have some gradient system. In your case, if it is local, it helps to calculate or not with gamma k.
Well, it's a solution of a certain elliptic problem. Yeah, I'll show you what gamma k's are, but I mean, what do you mean also that in Friedel-Wenzel it's not possible to calculate? It's not possible in some sense. It's not a simple expression in terms of some other function, but it's a certain feature.
In the gradient case, you can compute the quasi-potential, it's just the potential.
Yes. In some other cases, also it's possible when it's orthogonal, like when it's basically it can be if it's gradient H plus some vector field which is orthogonal to this. There are some cases when it is possible, but you're right. It's not an explicit expression in most cases.
Yes, but in your case, it is a bit simpler or not? The fact that you say that it is local.
It is expressed. I'll explain how to calculate it. It's a beautiful formula. It's not super explicit in the sense it's a solution of a certain problem.
Okay, I will see. Okay, thanks.
Yeah. But even in Friedmann-Wenzel case, it's a certain characteristic of the vector field, which, as you said, is not explicit, but it's, yeah. So, let me see. All right, so, so here I was going to had some slides about PD interpretation of these results, but let me skip those because I think here people in this audience are mostly familiar that if I describe some asymptotic behavior of a diffusion process, I can consequently describe the asymptotic behavior of related PDs, right? Parabolic or elliptic PDs. So let me skip that. Let me go to explain how those gammas how they are determined, okay? And let me look at one-dimensional example. In one-dimensional example, everything is completely explicit. Consider a process on zero infinity. So it is a diffusion process already. So this is the unperturbed diffusion process here. What is it? The coefficients are even constant. Well, constant. They're linear, but and then they're multiplied by constants. So this is linear drift and linear coefficient in the diffusion. So you may recognize it as geometric Brownian motion, right? So 0 is an invariant point. So the picture is like this. So 0 is invariant. And then you have diffusion to the right, you have diffusion to the left. Let's focus on the positive half axis. And then there are coefficients, alpha and beta. And the generator, you can write the generator, it's alpha x squared u double prime plus beta x u prime. Here, by the way, I write it in Ito form, but that's special because it's one-dimensional. Usually I'll stick to Stratonovich form. Okay, can we analyze geometric Brownian motion? Probably those of you who teach those kind of courses, say in graduate probability or introduction to stochastic processes, you can solve this stochastic differential equation. And the limiting behavior of the process depends on alpha and beta, on the relationship between alpha and beta. If alpha is larger than beta, so you have a lot of diffusion, then what happens is that the process will, no matter where it starts, it will walk around and will approach 0. So even if beta is positive, you have positive drift, so it kind of models a better than fair game, right? So here alpha and beta, okay, so even if beta is positive, so kind of think about investing money in you have a certain interest rate beta and you have a certain level of risk related to alpha. If alpha is larger than beta, despite the game being advantageous, with probability 1, you'll go to 0. And with tiny probability, of course, you'll be extremely rich, right? Because it becomes a sub-martingale, the solution. However, if alpha is small, it's controlled by beta, then you go to infinity. So you see that this point, the origin, is attracting or repelling depending on the relationship between alpha and beta. So, and this can be done explicitly. You can solve the corresponding ODE to see which direction you go to first, 0 or infinity, or you can, if you prefer to solve ODEs in a finite segment, you can go to 1 over delta, sorry, to delta or to 1 over delta and see where you go first. You can write the generator, solve the corresponding ODE, or you can just solve the SDE immediately to get the formula for the solution. So any questions here? So you classify attracting and repelling cases depending on the relationship between alpha and beta. Let me look at the multidimensional situation. And here I'll also introduce the perturbation, epsilon squared L tilde. So in general, let me introduce local coordinates. So I'll have, let me look at one surface, surface where diffusion process degenerates. And I'll look at coordinate y along the surface. It may be more than one dimensional. If it's two-dimensional surface and 3 dimensions, that y is a two-dimensional coordinate. And z is coordinate in the orthogonal direction. And I'll rewrite the generator of the process in these yz coordinates. So what do I do? Basically, I linearize everything with respect to the distance from the surface. This is the operator, just pure diffusion on the surface. This is non-degenerate, but it doesn't involve anything with z. So non-degenerate and along the surface only. Then I have z squared diffusion across the surface, z drift across the surface, and then mixed motion along the surface and across the surface with z. And this is higher order terms. These include z cubed d squared over dz squared, for example, things like this. So you may recognize some similarities with the previous one-dimensional picture. What survives? Similar to one-dimensional picture, you have this term and this term with alpha and beta. You see, let me flash the previous picture. You have diffusion and drift, which both degenerate at the origin because you have this factor x. And here you have diffusion and drift. Now this is the generator. So and now you have this alpha and beta. They depend on the point on the surface. So I explained this linearization, and let's look at the following. Can we say something analogous to the one-dimensional case? And analogously to the one-dimensional case, I can compare alpha and beta. But before, alpha and beta were just individual numbers, right? They determined whether geometric Brownian motion was attracting or repelling. Now, you have functions alpha and beta, but you have also motion along the surface. This motion along the surface, which is governed by this operator I called Ly. It has an invariant measure. Invariant measure, let's call it pi. Pi is the invariant measure for the motion on the surface, for the unperturbed motion, right? And then what I can do, I can average alpha and beta with respect to pi to get individual numbers, alpha bar and beta bar. Does this make sense?
Yes. Mm-hmm.
Yeah, so everything is okay, right? So I get individual numbers, alpha bar and beta bar, and I can compare them. So, and I'll call the surface attracting is alpha bar is bigger than beta bar. So the average, kind of the average drift, average diffusion across the surface. Well, diffusion across the surface is 0, but the linearization, the next order term in the diffusion, right? If the average of that is bigger than the average drift away from the surface, right? Then, then the surface is attracting. Otherwise, it's repelling. So we can already classify all the surfaces, but this is not enough. Because your question was, well, what was gamma? What is the characteristic number? How long does it take to get away from the surface? And here, it's not enough to look at this gamma, alpha bar, and beta bar. In one dimension, yes. In one dimension, for geometric Brownian motion, you can immediately say the speed of the speed at which you approach zero. But in the high dimensions, these two numbers don't contain this information. Instead, you need to do something more sophisticated, somewhat more sophisticated. This is kind of the heart of the matter. This little lemma. This determines this characteristic gamma. So I don't have an index gamma k because I'm looking at one surface at a time. So for one surface, there is this number gamma, positive or negative, depending on whether the surface is attracting or repelling. And this number is determined in the following way. There is a certain problem, sort of spectral problem that you need to solve. So it's kind of like an eigenvalue of some sort, except it's not exactly an eigenvalue because it's a non-linear problem in gamma. So here's the claim. Let's take one of the surfaces. Let's say it's an attracting surface, so alpha bar is greater than beta bar. And then there's a positive number gamma, which solves the following problem. This is the generator of the motion. We are talking about exclusively unperturbed motion for now. Perturbation will come in later. You solve on S. This is a problem on S. Operator applied to phi. Phi is kind of an eigenfunction of sorts, is equal to alpha. Alpha is a function, so we are talking about, this is kind of an elliptic problem of sorts. Alpha is a variable, so alpha depends on y. Beta depends on y. And phi is a function on S. And you need to solve this problem. So elliptic operator applied to phi is equal to this function with coefficient gamma times gamma minus 1 multiplying phi, beta gamma multiplying phi, and this is the first order operator. It comes from the mixed derivatives. So what this lemma does, it claims there is a unique solution, gamma, so basically you get a way to associate one number to each, here I wrote component of the boundary, it was basically because I was talking about PDEs, but to each surface.
So this term non-linear and gamma minus 1, the idea is that you make a sort of an ansatz, and this is a second derivative of this ansatz.
Yes, I'll explain. Yeah, it will be clear on the next slide maybe why I want gamma times gamma minus 1. But yes, so at this point, if you just look at this lemma and nothing else, okay, nobody prohibits me from making this claim, right, and proving it. It is not terribly difficult to prove it. It's one page in a paper, and then we repeat it in another paper just to make everything self-contained, because that contains kind of a heart of a certain argument. But basically what is...
I'm sorry, dy is second order.
No, dy is first order.
It's first order. Okay.
First order. dy, because it's here, it's this one. It's a local representation of the generator, and you see it carries z because it's linearization. But when looking at this problem, we don't have any z at all. It's just an elliptic problem on the surface. And what it does, it associates an individual number to each surface. What plays a role? What plays a role is the behavior of the unperturbed system, right? Because this Ly is it's the operator of this unperturbed system on the surface. These alpha and beta and d, they come from linearization of what happens near the surface. So it's not only behavior in the direction of the surface, it's how fast you degenerate as you approach the surface. how fast those vector fields degenerate.
Such a gamma is also unique, or is the smallest, or something like this? Is it
It's
unique?
Unique. I guess unique non-zero, because you can have gamma equal to 0 and phi equal to a constant.
It's integer, as I remember, I think.
Pardon me?
Is it an integer?
No, gamma, I don't think you can say anything about gamma other than its unique solution of this system.
Okay.
Yeah. So, what is the role of this gamma? The idea is that, you see, it's not only equation of gamma, it's also on phi. It's a pair, gamma and phi. Phi is a function, it's a, say, positive function on the surface that solves this, right? It's kind of has the same flavor as eigenvector and eigenfunction, right? Except it's because there's a quadratic term, it's not, I don't call it eigenvector. The idea is that if let me look at the process. Our original process was called X, but I'll write it in components, component along the boundary, along the surface, and component in the orthogonal direction, Z. And this pair, YZ, let me plug it, phi of Y, Z to some power gamma. And with appropriate choice of phi and gamma coming from the lemma, this object becomes nearly a martingale. So basically what happens, it turns out that if I have a surface, if I study the behavior and the direction across the surface, by itself, it's not a martingale, but if I take it to a certain power gamma and I modulate it by phi, it becomes nearly a martingale. Nearly in what sense? If I toss out the perturbation, if I toss out everything except linearization, then it's a pure martingale. But otherwise, it's nearly a martingale. And the reason for that lemma is basically I say, okay, I want to see a martingale somehow. Let me look at this guy. If phi and gamma satisfy the lemma, then I see a martingale. That's the point. And if I see a martingale, I can talk about how long it takes to get away from the surface, how long it takes to get to the surface, if the surface is repelling, etc. So maybe let me go to the previous slide. For example, if I start at the surface, the time to leave a small neighborhood scales as size of that neighborhood over epsilon to the power gamma. So we can make a correct asymptotic statement out of that. So that answers basically the question of how the transition times are determined. They're determined by solving this problem or by looking at what makes this object into a martingale.
So sorry, is it easy to make an example where everything is analytic, so smooth analytic, and gamma is not an integer?
Gamma is not an integer. Yeah. Even, you see, gamma in the one-dimensional case, what is gamma going to be? In one-dimensional case, it's going to be 1 minus beta over alpha, alpha over beta.
Okay, I was confused. Okay, thanks. Okay. I was confused. Thanks.
Yeah.
But also, just a small question. You also need, I don't know, in some long time to be almost a martingale, right?
No.
No?
So it's so when I said it's nearly a martingale, it's I mean, maybe it's a little bit of an overstatement, right? Because it's a martingale as long as Z is small. So if what I can say that this
kappa. Okay. Once you homogenize Y somehow.
So it's a martingale. I mean, I don't homogenize immediately in the sense I need to still include this function of y to make it a martingale. But sort of intuitively, the distance from the surface is almost a martingale up to some small kappa. Of course, the larger the kappa, the larger the error. It's not going to be a pure martingale if I go further away, right? And also, I need to treat a small neighborhood, a size epsilon, separately, or epsilon times some large a, because there the perturbation will spoil things. But in this crucial zone where I can use perturbation to get a little bit away from the surface, and then I don't see the major effect of the original unperturbed diffusion. Everything is determined by linearization in this zone. And this determines how long it takes to get away from the surface. For the, say, for the perturbed process, it takes this time. So let me see, what does this say? I mean, this maybe just repeats kind of with some more precise notation as to what we did, right? And then how does one understand the metastable behavior then? To understand metastable behavior, you see, in the case of a Markov chain, we need transition. Remember the very, very first slide. A Markov chain, 2 states, or maybe more than 2 states. Markov chain, what is interesting about it, even if it is parameter dependent? To define a Markov chain, even in 3 states, right? You need transition probabilities, essentially, right? Maybe you go here with probability or with intensity epsilon, and you go here with intensity epsilon cubed, right? And then, okay, it turns out you need to wait much shorter to go from 1 to 2 than from 1 to 3, because epsilon is much bigger than epsilon cubed, right? So, but you see, I just drew one number per error, right? This number determines the transition times and transition probabilities. You know how long you'll need to wait to escape from the first location. You need to the time in the pure Markov chain is exponentially distributed, right? Basically, you sit until an exponential clock rings, and then you toss a coin, right? So everything is intertwined. Transition times and transition probabilities, they're determined by these numbers, epsilon squared, epsilon cubed, right? Or even if it is discrete time Markov chain, you just, every step you look at these 2 numbers, epsilon cubed, or you just stay in place with probability. You stay in place with probability 1 minus epsilon cubed, and that's it, right? Now, for more sophisticated systems, these are not pure Markov chains after all, because you have, okay, you can talk about how long does it take to separate from a certain surface or to exit a certain state, but then where you go is determined by a completely different set of data. And it very well may be that transition times and transition probabilities are unrelated in some sense, or maybe they're related, but they're not independent. So maybe if you decide to go to state 2, you need to wait one time, and the probability and the time are some strange relationship. So in our situation, we need to understand the time to leave a neighborhood of each SK. And we need to understand transition probabilities between SK. Where do you go? So where you go is, let me just draw a I think I'm almost running out of time, right? I mean, I wanted to maybe say a few more words about the general setup. I'll not talk about it directly, or sort of not talk about it in detail, but before that, concerning our situation, we have finitely many surfaces, right? S1, S2, S3. We managed to separate by a certain distance, kappa. At this point, what happens? At this point, you can already forget about perturbation. At this point, of course, you may do many of different things. You may go to back, which will happen with overwhelming probability. But if kappa is small, but epsilon independent, you may talk about probabilities of transitioning to S2 or S3. Here I'm talking about the situation where surfaces are attracting and they themselves serve as metastable states. And the distribution will be between neighborhoods of those. The situation where you have repelling surfaces exclusively, then metastable distributions will be measures inside those surfaces. And this is the most recent paper that we are completing with my graduate student, Chenglin Liu. But coming back to the attracting surfaces, how do you decide? Do you go to S2 or do you go to S3? What is the probability? Here you can actually make an explicit calculation in some sense, because you have xt. This is unperturbed process, right? And let's consider a new process. Xt tilde is xt conditioned on not coming to S1. You can take a diffusion process conditioning on doing this or that thing, and it's going to be a new diffusion process. It's so-called dupe transform. So something went wrong with my page. Anyway, here. So basically the transition probabilities are given by this dupe transform of the original unperturbed process. And then what happens then? Then we know the transition times and transition probabilities. We get in a Markov chain-like situation with that I almost started with, except it's not Markov chain per se, because as I said, the transition times and probabilities, the relationship between them may be very non-trivial. So you end up in a situation described by a so-called Markov semi-Markov process, or Markov renewal process, semi-Markov process. So and then what is a semi-Markov process? I don't know. So should I finish now, or take 2 minutes or 5, or what should I do?
Or maybe 2 or 5 minutes is okay.
2 or 5 minutes, okay. So semi-Markov process is the following thing. Let me see if I can get. Can I get just a new page somehow? Okay, maybe what I'll do, I'll stop this screen, stop sharing this screen. I'll just stop share. I stopped sharing, right? Yeah, and then I'll share just a whiteboard. And so let's assume I have S1, S2, S3, and then I have the following object. I have from each state, I can jump to another state. So I can talk about probability that x1. So let's say discrete time starting from any point x belongs to this or that state. S2 is known. It depends on epsilon. These probabilities depend on epsilon. But that would be like a Markov chain, right? I know where I'm jumping with which probability. Maybe not S2 to Sj. Right? Maybe I can even say to A, which is a subset of S2, right? So I can jump from one location to another, but also there are times associated with it. Probability that time for the first jump associated to some initial point belongs to some interval, whatever S1, whatever T1, T2. Conditioned on jumping to A. No. In a pure Markov chain, if you know the probability of a jump or of where you go, you know the times, because times are exponentially distributed random variables. Here, they're just some random variables that depend on epsilon, and they're known and depend on epsilon. So what do you need to know about these transition times and transition probabilities in order to be able to say, okay, we have certain type of limiting behavior that after a large time, I'll know where we'll end up. So what do we need to know about those? In order to say that maybe after some long time, what does mean long time? Here, each jump takes time 1, as we said, right? But there is a t associated to each jump. So we can build a continuous time process, which works like this. You sit, but instead of sitting for time 1, you force yourself to sit for time t1. Right? So this new process called semi-Markov process obtained from this pair is called let's call it x tilde t epsilon. To get x tilde, to get limiting distribution for this. Okay, I'm explaining. It's not very lack of detail is not even the right word. I'm just throwing in some concepts, and those who have not seen semi-Markov processes, maybe it takes a little bit of effort to get used to it, but it's not a big deal. So here we can have results which say, okay, what are the conditions? What are the abstract conditions that guarantee some kind of metastable behavior? One type of condition is that there's very little dependence on the initial point if this point is confined to one of these sets. For example, in the picture with surfaces, it should not matter very much whether you start at one point of a surface or another. It's just transition between different surfaces that matter. And another set of conditions concern the asymptotic behavior of these transition times and transition probabilities. They should stabilize with epsilon. They should all scale in a similar way, so all as powers or all as exponents, or be commensurate in some sense. Okay, so there's the whole subject of a whole different paper that I wrote with a graduate student, Ishfaq Mtias, a former graduate student, but I didn't have time to get to that much, so I'll leave this portion kind of unfinished. So now I'll stop here.
Okay.
Okay, thank you very much.
Thank you. Could I ask a question? I wonder what you think about the following problem. For simplicity, consider that the time is discrete. It's not a big deal. Okay, associated with any state of your metastable Markov chain infinite dictionary. Okay, and suppose that every moment you are in this state, you draw a word from this dictionary. Okay, this is my extension of Turing problem. Turing, if the state is only one state, right, one dictionary, and you're looking for number of words with which appear the first time, this would be the Turing problem. So something very famous, a very old question. Okay, and now is a big progress now in this direction. And the question is how to write the limited process that you are going along your metastable chain, and you count the number of words that you see for the fixed number of times. So you fix K, and you see, you count the number of words that you met before K times. Okay, and there is a big progress in this problem now, but no, not specifically for the metastable case. And what you think if this could be extended? How interesting it's for you to discuss extension of this technique for metastable Markov chain?
Well, I would have to understand a little bit better, so I'm not familiar with this Turing problem, unfortunately. I would guess it's has some elements of statistics, right, to determine. Basically, you have dictionaries.
The basic question is, the original question: how many words Shakespeare knows that didn't appear in his plays? Okay, the original question: how estimate the total number of words that he potentially know but didn't use? This the first question asked some 50 years ago. Okay, and now in big extension, big development in this direction. And if you are interested, we can discuss in more details because my impression is that it may be interesting to specifically study if you have a number of dictionaries, right? And you have a metastable Markov chain of these dictionaries. And you look at different time scale and look how the number of words you have seen fixed number of times. And the limited process, the joint distribution of this process, this is a very, I think, interesting problem. And there is some ideas.
Yeah, it would make me curious. I mean, I would have to understand the setup better. But I mean, say, how would you know how many words Shakespeare knew? I would guess you need to take some other authors, right, and study.
No. You use only the set of his published plays, nothing else. Okay, you don't know anything else. You know only the text that he actually published. Okay, and then basically database you should make a judgment how estimate the number of words that he knew but never used. Okay, that's the original Turing question.
Yeah, so basically try to limit the consideration at first to some small portion of his work, see how many new words you get if you add a new work.
Okay. If you're interested, we can discuss it later. But you understand the point, yeah? You got it.
Yeah, I mean, in general terms, yeah, I would, yeah. But yeah, it would be curious, yeah, sure.
Okay. Thank you, bye-bye.
What is known about the case alpha equals beta?
So alpha equals beta is, well, in some sense, well, we didn't write it in any case. We didn't include it in the papers, except one paper where we talked about solutions of elliptic PDEs, in which case it's so it has some common features with the attracting case where alpha is bigger than beta. in the sense that, okay, one-dimensional Brownian motion, it will not go to zero in some sense, but it will make infinitely many excursions arbitrarily close to zero if you give it enough time, right? So let's say we're looking at dxt is equal to x dt plus x dwt, something like this, right? Or 2.5. Let me see, I already forgot. Like this, 1/2 or 2. This is the critical case, right? So the process starting on the right will not go to infinity or zero, but will kind of oscillate infinitely many times between 0 and infinity. And you can use this fact to solve elliptic problems and to say that, okay, if you include a small perturbation, you can try to calculate how long it will take to get to distance epsilon from the origin, in which case the perturbation will already start playing a role. So but for the purpose of describing metastability, I think we need to give it a little bit more thought. I mean, there are definitely some technical parts in this analysis of metastability, transition times, which rely on this gamma having a particular sign, plus or minus.
Gamma equals 0 in this case.
Yeah, now gamma is 0, right? So it's so intuitively it will. So whatever happens will resemble just geometric Brownian motion with gamma equal to 0, right? One-dimensional. But technically, I'm not sure it may be somewhat non-trivial. So it may be a worthwhile thing to look at. Still. Do these surfaces even serve as attractors, for example, right?
Because it could be no local problem, right, for gamma 0.
For gamma equal to 0, well, for example, what if there are higher order terms? So let's say it's x dt plus, I don't know, x to the 5th dt plus 1/2 x dwt, right? Or minus, let's see. So does 0 still serve as a metastable state at some time scale, right? And if so, at which time scale? Before it was used to be, if it was not x dt, but 1/10 x dt, right? This diffusion would prevail. It would kind of push it towards 0. And you have a certain power, time to get out of the neighborhood of the origin scale. There's some power which is related to the magnitude of these coefficients, right? But if these coefficients exactly match, where it's like gamma is exactly 0, right? Then maybe the next order coefficients will play a role, and maybe the time scales will change from powers to powers of logarithm, for example, right? I'm just like making wild conjectures. So maybe it's a worthwhile thing to look at if I don't know how easy or difficult it may be. Hopefully not terribly difficult.
Okay, thank you.
In some cases, to describe the asymptotics of an elliptic problem where metastability basically was not playing such a role, we treated case gamma equal to 0, but sort of otherwise we didn't.
Okay, then thank you very much for your talk, and
Thanks.
I think that we finish now.
Yeah,
Yes.
thank you for
Thank you.
coming a bit
Thank you.
late hour.
Thank you. Thank you. Thank you.
Thanks.